So, welcome back to the third session, the first session today, but the third session of FABRICATE, LOCALISE Sourcing and Performance. And it's my great pleasure to introduce Leslie Lok, who will be chairing the session. Leslie graduated from the MIT with a Master of Architecture and is now an assistant professor at Cornell University in the Department of Architecture, where she directs the Rural Urban Building Innovation Lab. Her research and teaching explore the intersection of technology, novel material methods, and urbanization. And her work contextualizes design strategies with computational protocols and mixed reality technologies to develop novel forms of making and adaptable housing designs in rural urban contexts. Leslie is also a co-founder at Hannah, and we were introduced to Hannah's work with the collaborators yesterday in her paper presentation. Hannah is an experimental design practice that operates between material and urban scales, utilizing innovative forms of construction, such as 3D printing of concrete, as we saw yesterday, to robotic fabrication and other advanced building practices. Hannah's been the recipient of many prizes and has also been exhibited globally. And your work has also been published, not just in FABRICATE, but also the kindred events, Robark and Acadia. So, Leslie, welcome. The floor is yours.
Thank you, Phil, for the kind introduction. It is my great pleasure to introduce the third session of FABRICATE 2024 conference called LOCALISE Sourcing and Performance. Etymologically, the term local is defined as pertaining to a place, an identifiable spatial condition or spatial form. To be local implies to be a part of a whole, yet to remain uniquely identifiable and differentiated. Locality engages with place, or perhaps better context, be it communal, social, political, environmental, ecological, or material. Within our increasingly global communities, questions of locality take on new meanings and urgencies, offering a much-needed alternate readings or points of view for the creation of resource-conscious research and architecture. As my colleagues at Cornell, Andrea Simic and Val Work, note in their book, The Language of Architecture, and I quote, "Every architectural work exists in the presence of a chorus of contexts that can impart meaning to, and in return derive meanings from the association with the work," end quote. We shape our localities, and in turn, they shape us, and vice versa. The 4 papers in this session engage the notion of localization and context in a variety of thought-provoking ways, across scales, geographies, communities, and material systems. In framing secure water, resituating the water-energy food nexus within recombinant building envelopes, Mandi, Pretorius, and Dyson state that, quote, "Out of necessity, informal settlements across the globe will lead the way towards novel circular, renewable resource economies," end quote. Light, thermal qualities, and water are co-shaped by material systems and fabrication methods within the aim to increase household water safety. Emmanuel Vercruysse and Catie Davies' research, Foraging for a Field Station, Cultivating Material Efficiency, engages local forestry practices and waste materials by utilizing byproduct of timber harvesting to develop new construction methods, structural timber roof systems. And the work, quote, "leverages the inherent strength of round timber and elevates the connection details of what would otherwise be considered as waste product to furniture-grade levels of craft," end quote. And also, in Catie Newell and Zackery Belanger's long-range intrinsic acoustic performance, quote, "reshapes glass at a variety of scales to invoke gradient of acoustic behavior, such as reflective, diffusive, absorptive, and transmissive," end quote. Their work engages forms and forges acoustic spatial experiences in synthesis with localized material transformation in glass. In Sandy Curth's research, the fourth presentation in the session is called Sueños con tierra y concreto, mean dreams with earth and concrete, multi-material fabrication for low-carbon construction, an optimized floor system for affordable housing in Mexico. Their work, quote, addresses the global need for affordable housing construction through a contextualized approach to material-efficient design and fabrication of building systems, end quote, by developing a shape-optimized beam and block floor system. Noteworthy across all projects is the engagement with the local creates and how these methods promote new measures, metrics, and benchmarks for performance. In Farming Secure Water, drawing from Anna's evocative description in her keynote yesterday, like a biomechanical Frankenstein, light and air are localized resource and also a metric of performance to shape and manage water. In embracing a scavenger ethos, Foraging for Field Station reclaims and repurposes. The approach does not merely recycle but reinvents. When performance is manifested in the replicability of non-standardized components through technological and computational means, while long range explores a more abstract yet highly precise interpretation of the local, wherein geometric programming serves as an active system for localizing acoustic performance tuned to space. And in Dreams with Earth and Concrete, Sueños con tierra y concreto contends with local building codes as a subset of performance. In these work, reciprocity between different stakeholders and communities is often the main driver for research and development. And across the board, the 4 research projects also engaged in highly localized means of material sourcing, adapting to given contexts and environments. I look forward to the session's presentation and the following conversation. First, please help me welcome our first speaker, Mandi Pretorius, from the Yale Center of Ecosystems and Architecture, with their presentation addressing water, energy, food nexus within buildings, shaping light, water, and energy flow.
Thank you. As Anna introduced yesterday, we are the Yale Center for Ecosystems and Architecture, and we really are interested in environmental resource flows in and around buildings. Shaping these, particularly as we're talking about today, aware of the great degree of interdependence between our water, energy, and food systems. That is actually problematizing many of our urban infrastructures, our regional availability of resources, and leads to greater insecurity at the household scale. So we focus on the household scale within context of architecture and buildings because of greater security. So to start, we start with the premise that we should acknowledge to what an extent, to what great degree the built environment shapes our resource flows. Not only if we recognize that by 2050, up to 70% of the urban population, well, 70% of the global population will be living in cities, but also to acknowledge that the great degree of centralized large-scale infrastructures that make many cities possible are shaping the availability of resources in an environment and shaping who gets access to what and at what quality. And this is highly problematic if we're going into a space and age of increasing scarcity. So there are 3 main factors to consider when we're thinking about water security. And now we start with water security for the sake of household water, energy nexus, water, energy, food nexus in households as a starting point to then understand the relationship with all the other resources we need for basic needs. So the 3 factors really are what Indy has now retermed as climate breakdown, and we're truly acknowledging the impacts thereof. The failures of centralized infrastructures, they are costly to maintain, they're damaging our environments, they are really not capable of being expanded to cover the global water access we need. especially if we think about it in the context of the rise in urban populations, but also the rise in informality, where up to a third of the global population will be living in informal settlements by 2050 by current rates. So now if we're responding to, say, for instance, the call to greater net zero energy and water in buildings, as we are, what about the majority of the globe, where perhaps mostly living in the African continent, for instance, where we are seeing a different range of constraints and a different range of potentials? And how do we develop means that we can achieve on-site water and energy in more conditions, more housing typologies, more climates? So therefore, we're focusing on developing distributed approaches to doing just that, but really focusing on informal contexts where there is really a range of opportunities and informal flows. But to start, let's go back. So now, there's a number of paradigms we've inherited that really drive how we design, how we think, and really the emphasis we see today on centralized systems, water governments that is top-down. And if we look back, there was a prior time in pre-modern waters where water was more attributed with life, qualities that stemmed from where it was sourced. And incrementally, we've shifted towards more in the modern period where we've quantified water. We've extracted it and flattened it to a sense where it's an environmental goods and service. And that has really been leveraged with large infrastructures that are now problematized by climate variability, because our water and energy is tightly tied. So greater degrees of water insecurity impacts our hydroelectric power, and our water systems are very energy intensive to deliver water to your home, never mind the great amount of leakage. So shifting to a decentralized, distributed approach to water management is already being discussed in the discourse, and emerging science in water treatment as something that is essential. And then we're also saying we need to think about this in terms of global communities that have different range of accessibility. So to start with, developing open architecture frameworks. We will present one, and the interest is really in developing typological forms, typological behaviors that we can foster within the built environment, using existing and emerging materials and processes towards greater distribution, adoption, and replication. By replication, we mean this can breed its own life. It can go do what it needs to do in all the different contexts that has happened place. So to step back again, the framework we're working within is an area of research within our group called the Solar Enclosure for Water Reuse Framework. It is ongoing research that imagines many different types of physical embodiments of the framework that could take place or really shape resources within different environments and different climates in response to the built environment of that place. So for instance, if we really think about it as a framework, how does it work within existing or new builds? How does it work within existing typologies or local assembly logics, for instance? And I should go back to say what it really is doing, and get to the major point. It's offering ways that we can shape environmental resources in and around buildings, but functionalizing it for plural purposes as opposed to just using our walling systems as a form of enclosure for our hermetic environments, but actually shaping light for instance, shaping solar energy for water treatment, as is shown here, concentrating that energy to functionalize for different processes, but then allowing some of it through for daylight. What I need to get to the point of here is that in this framework, there are different ways that we can introduce shaping through concentration methods, be it through application of optical geometries or different surface treatments, that then can slowly be directed towards particular functions. And in this case, we're looking at a lot of photochemistry because we're looking at on-site water treatment using renewable energy. So multivalent resource pathways. One of the major issues with single function systems is the fact that they're single function, and they're also really dependent on a certain kind of input material. What if we think what if we think in terms of an ecosystem's set of resilience factors, which is a greater degree of redundancy, a greater degree of multiplicity. So what we're looking at is generating multiple resource pathways using bioavailable material-based mechanisms to increase the likelihood or the capacity to produce food, treat water, and capture energy on site. So, multiple resource pathways towards guaranteed household water security. What we mean by multiple resource pathways in this exact approach is looking at the context of a place and actually better matching the available resources to how we're treating our water, for instance. Many systems are abstract, large scale, they're really chemical and energy intensive, and they're kind of dependent on that same quality of energy year round. Perhaps more, perhaps less, but you're never really qualitatively looking at seasonally, locally, what is available. So to better match available soil energy to how you're treating your water, and in terms of the plants you're seeing here, to better match the chemistry with available sources of that chemical compound. So in this research, we're investigating a bio-based means of enhancing solar disinfection through a plant-based dye that you can source from a range of food-growing plants that assist with photosensitizing and creating reactive oxygen species that kill waterborne microbes or waterborne pathogens, and is particularly good with viruses. It can be sourced from a range of food-growing plants that also seasonally might change. So seasonally, you might be sourcing that particular dye from a different plant. Multiple resource pathways, that's what we're trying to get to. And I should also say that in looking at water treatment, we're looking at multiple ways of using solar energy. So spectrally, it is qualitatively diverse. We can use parts of the UV spectrum, you can use the broad spectrum, or as with the dyes, we're using particular aspects of the visible spectrum. So to leverage informal resource flows, building materials, assembly logics, and use practices already in place to introduce capacity for on-site water management. So our focus really with the proposition we're going to be showing today is leveraging exactly what's already available to develop means that what's already available could be augmented for potential ways that we could actually do more and towards on-site water security. So decentralizing access by bridging material flows and across informal settlements, we can see these are photos taken from one of the field sites where this research has been investigated, is still being investigated, in the Lake Atitlan region of Guatemala. I should speed up, but what we were really taking away is the fact that there are all these existing materials that can really inform the design proposition. And energy in the built environment, recombinant assemblies that metabolize the built environment. How can different embodiments respond to the particular localized informants of a place? So here is a matrix of different embodiments that could potentially be generated from different fabrication processes, be it forming, rolling, casting, or in the last case, extrusion. And each have different aspects of how they're interfacing with sunlight, how they're interfacing with the building, and how there's optical geometries embedded into the system that then leads to different conversion processes, right now for water treatment, in other cases for energy processes or ambient water harvesting, for instance. So as an overview, and to step back into looking at household water security, when you're thinking about many limitations of current point-of-use water treatment systems is that they're really dependent on input materials, they're really dependent on energy. So for instance, boiling is widely used. It's the greatest, it's the most common water treatment practice, but it's really dependent on some form of fuel. And many times households don't have that, so they cannot treat their water on a daily basis if there's a sense of resource scarcity. So cumulatively, resource security needs to come as a considered integrated practice. So this proposition is integrated into the roofing of conventional a conventional typology, which is your corrugated roof sheet. It is interfacing sunlight, both to treat the water and also to allow some daylight through. It is achieving, at certain parts of the year, with sufficient solar water heating to offset energy bills. And it's safely treating water year-round using several disinfection mechanisms. Principally, it's an optical geometry that is integrated into the existing kind of logics of a corrugated roof sheet, scaled appropriately, but also as opposed to using, and in this case, because it's a reflective optical geometry, instead of using metallic reflectors, what we're doing is everything is in the form of lightweight extrusions of some kind of form of dielectric formable material. The initial proposition might be conventional polycarbonate. In the future, we're working towards bio-based plastics that could be hardy enough to withstand weathering. The 3 disinfection mechanisms are common. You're familiar with them. Solar pasteurization through heat, using broad spectrum sunlight. Visible spectrum photosensitization using the dyes I mentioned, and then UV disinfection. And so what this diagram is showing is really how you're shaping the energy for multiple uses, including interior daylighting and water heating, without solar heat gain to the building interior. So initial testing of the plant-based dyes looked at the scale-up of the reactor as an engineering prototype that really started looking at the photochemistry. You'll see from the diagrams there's a lot of pink, and really that's just one of the dyes. And the point of the dye is also that with photodegradation, the rate of photodegradation matches the rate of water treatment, so it's a visual indication of when the water is safe to drink. So as a brief overview, all prototyping and experimental testing considered realistic factors of types of materials we'd actually use, types of environments we'd actually be working within, and iteratively, all simulation and physical testing was part of the design development that kept to finding possible ways of achieving what we needed using the available materials. Oftentimes, when you have a multifunctional system, you have numerous trade-offs between one function versus the other, and this is actually the richness when you're thinking about something in an ecosystemic approach. So the experimentation and the field testing was conducted between sites in the US, water-scarce regions such as Phoenix, Arizona, Cape Town, South Africa, which is prototypical of a kind of emerging economy with hybrid formal and informal aspects to the city, and Lake Atitlan in Guatemala, which is more rural, and the centralized infrastructure is completely failed and people cannot drink the tap water. So in Phoenix, we did a lot of the laboratory-based testing, where we looked at really the design development stages of figuring out which configurations would work in what type of context that would then assist with modeling later. We did a lot of the thermal testing in Cape Town, South Africa, especially in this climate. There's failing energy infrastructure, and therefore solar water heating is more important. And then in Lake Atitlan, we actually paired water quality testing and a study of household water treatment practices inside with testing for viruses and microbial inactivation. And now to come back to the daylighting aspect, really then understanding how you're shaping light, and here you just see a little bit of light coming through, but this can dramatically reduce energy consumption, can contribute light to a space, but it doesn't contribute to glare. So in closing, the work is ongoing, and we are working towards scale up to architectural scale test beds, where we'll look further at not only the system functions, but then the qualitative aspects of daylighting and the impact on the sense of self and personal well-being. Thank you. And just to lastly say, this is a multidisciplinary collaboration between several universities, between optical engineering, thermodynamics, environmental chemistry. Thank you very much.
Thank you, Mandi. I would like to welcome our next set of speakers, Emmanuel, Vercruysse, and Davies from the Architectural Association to present Foraging a Field Station, Cultivating Material Efficiency.
Which button do I press, Phil? Oh.
There you
Okay.
go.
Okay. Let's go back. Hi, everyone. Thanks for having us. Emmanuel and I have come from the Architectural Association, where we run the Hook Park campus, and we co-direct the Design and Make postgraduate program that's residential at the Hook Park campus. I'm just going to give a bit of an overview, a bit of context for the project, because we think it's really important, before Emmanuel's going to go into the more specifics of the specific research project itself. So a bit of context for Hook Park. Hook Park is part of the Architectural Association, but it's about 4 hours away. It's a kind of satellite campus based in the southwest of England, in Dorset. It's set within a 330-acre woodland, a managed woodland that we harvest. And the Architectural Association owns that woodland. So kind of a weird thing for an architecture school to own a woodland, and also kind of a magical and amazing thing. So within that, the architectural campus, which has a small cohort of postgraduate students and a rolling program of visiting students from the main school in London, operates as a kind of strange laboratory. When we talk about it at the main school in the AA, we tell them this is where the wild things are. And it's got a kind of air of the weird about it, we hope. It's really important that the whole site, including the 330 acres of forest, is the laboratory in its totality. And that the landscape is included in the conversation, is a really important part of Hook Park. This is a kind of diagram of the various tree species we have in a managed woodland at the moment. It's about 17 different tree species. The big circle in the middle is where our campus is. The little circle is where our timber production facilities are, our sawmill. Predominantly, it's Norway spruce and beech. And really what we want to talk about today is broadly the fact, this is a magnificent species. This isn't one of our trees, by the way, but for illustration purposes, trees are incredible things. They do incredible things, and way obviously beyond timber yield. But even if we talk just about that, they have in their natural geometries obviously an incredible structural integrity. And we're going to talk a bit today about all the little wood at the top, all the crown timber, which is makes up something like 20 to 50% of the above ground biomass in a tree, but is rarely a part of the timber production process. We're probably more used to thinking about timber like this. And when you think about the natural geometry versus this kind of standardized timber, you're really amputating most of the structural integrity when you're planking woods up for dimensional timber. And I think it's interesting to think up in a place like the UK. We're one of the most tree poor nations in the world. I think something like 45 trees per person. I think in France it's 200 and something. Quick Google this morning, I think Denmark's between 100 and 150 trees per person. It's a pretty important thing to think about. Well, how can we be more efficient with the resource that we have, in advance of obviously trying to plant more and create more of a resource in the future. So how can we make more use of the whole tree? I think the other really important thing to say about Hook is its interdisciplinarity. So this is our forester, Chris Sadd. He is integral to the program. It's an architecture program, a Masters of Architecture. But it's really important that we're having conversations across disciplines with forestry, with engineering, with ecology. And that kind of interdisciplinarity is really, really key. And these are conversations, particularly between forestry and architecture, that aren't really had. Those people don't really talk to each other, which is strange. So an architecture school that owns its own forest is, like I said, amazing. We are in control. We run our own sawmill. We have the academic and the research programs at Hook have an amazing opportunity to operate across the full spectrum of timber supply chain, and to innovate and to kind of interrogate that supply chain from sapling to building. And the students are, it's a huge part of their conversation. So for them, the origin of the timber for their buildings is not the timber yard, it's the sapling. So here we are. The forest, the campus, is both, weirdly, its own material library and a site and a context for the work, for the architecture. And I think it's a kind of very tiny microcosm in forestry scales, but a microcosm that enables us to think about the hyperlocal. Our material travels meters to get to our buildings. And it enables us to have a conversation in relation to very long time scales. So we also have a forest research project ongoing at Hook called Wood Lab, which is looking at a 100-year strategy for planting for our forest, which engages with climate change resilience and different types of species that we'll need to plant in relation to that. And nesting an architectural conversation within a landscape that is able to have this longer term frame of reference, I think is really, really important. So just to kind of outline the brief that we gave for this project, it was 10 MSc and MArch design and make students were involved in this project collaboratively. The collaborative nature of that is really important as well. They were asked to make a shelter for our forester and forest researchers, local passing walkers, and an outdoor space for teaching. And it's set kind of conceptually to be a witness to a changing landscape. So it's set in a place on the site that has a uniquely for the site a kind of view out to neighboring landscapes, which are undergoing a kind of rewilding program. So not only our own site, but relating landscapes are kind of undergoing this system of change. And we asked them to use zero value crown timber that is a byproduct of the harvesting process.
Right. Thanks, Kate. So this is the structural logic of the field station. If you could just about make that out. It's a demountable roof structure, 100 square meters, that sits on 3 columns. It doesn't use any permanent mechanical fixings or glue, so it's designed to be demountable and reconfigured. So there is 2 layers of cords, horizontal cords, that are actually pressed together by a threaded rod. That means all the diagonals are in compression. And this is a section through the structural logic. We work very closely together with Arab, so they help us structurally analyze the system. These values, they're quite interesting. So these are the locations of all the threaded rods. They have different newtons they need to meet from a tension point of view. So the structure is really supported by an engineering logic. But this is really the star of the show, which is the 50 to 90 mil diameter round wood. We needed 256 of these. They're all unique in their geometries. It's important to state that we learn through making. So we start with a low definition model, which is generally held together with duct tape and some glue. And we work through generations. So we identify the problems and try to resolve them in the workshop. So for the field station, this meant we made 7 generations to get to the final building. So this is us exploring and learning and making mistakes. But really, it starts with a connectivity with the material and an intervention within the production chain of timber. So this is an industrial harvester, very intelligent machine that roams through the forest, but is guided by industrial data. So as it cuts down and strips the branches, it will actually measure the diameter and cuts it to optimize length. this is what's left behind. So as Kate said, there's about 40% of these beech trees are left behind. These are the branches. So the challenge for our students is to perceive this or work with this as structural material. So here are some of our students out, like scavengers, foraging for material, of leftover materials. When you go out into the forest and you source the material, there's an initial form of grading. You need to cut it. You go out with your little jig to get the right diameter, but you also check for defects in this harvesting kind of process. So on the left, you see your standard geometry. This is what, on the right, this is the geometry that we need to get to. We need to get these really quite straightforward tenon connections. And to do that, we developed a bespoke robotic flow. So we did this together in a team with Wyatt Armstrong, who's our robotic developer, who's in the room here somewhere. He's co-author for this article, and with Gary Edwards, who's a specialist in rod. But this is the setup. So we have a feeder station, a 3D camera, and a circular saw. So the robot has a gripper as an end effector that picks up the branch. It gets scanned, and then the part gets taken to the tool, to the circular saw, which is mounted on a lathe, as you do. So this is an animation. Oh, here we go. So this is the process. So the scanning is really important because, as I mentioned, there's 256 of these. They're all unique. To turn this into a standard component, that's really where the research resides. So this animation really shows the geometric variety in all these components, and talks about the process of the coding. So the scanning allows us to draw a central line through every individual piece and allows us to reposition the tenon. So the tool part for the robot get updated in the process. This all happens live. Wyatt managed to optimize the script. It took us about 2-3 months to develop the application, and in the end, Wyatt got it down to 6 minutes per component. He made a hole in the door every 6 minutes. One of these components poops out of the robot cell. Oh, sorry. How do I go back? No. So this is quite a nice little film of a component getting cut on. Shows the indexing of the circular saw, but I will skip through that because I've got 2 minutes. But the indexing of the circular saw is really important to optimize the tool part. But these are the machine components. This is a flat-packed field station as components. We took all this on site. We spent 2 glorious weeks on site. This is our site of production, really, for Assemble. It was actually quite a complex logic to put this together, but the whole team went out on site to assemble, and this shows a little bit of the logic of how it all weaves together. There's a bit of variety in components because the 3 columns need to take the load. This image shows the contrast between the natural geometries and the engineered timber, the machined, the milled timber. So the roof weighs 4 tons, so we got a 55-ton crane to lift up the structure and locate it on our 3 columns. And some views up into the structure. If it is assembled, it's kind of its current state now. We're also interested in the longevity, so we're interested in maintenance and repair. All these components are being compressed, so you can't just release them. But we looked at a prosthetic little intervention to be able to replace components if they do rot or break. This is some of the magic views out into the further landscape.
So I guess just to conclude, 29 seconds. I think it's important to us that the forest dictates the material parameters, so it's a kind of inverted relationship, if you like, in this kind of localized approach to material supply. Foraging for us was the word that summed that up the best. This idea of taking what the forest offers as a gift, the forest offers a gift, and working with what is readily available locally as an approach and as an attitude, that this is a prototype of both a kind of technical system, a material system, but also, we think probably more importantly, a way of thinking about things.
And maybe just to add, this is the result of teamwork. So there's a student cohort, there's staff. We work together with the forester and Time's Up and Arab. So this is team effort, which is really important. One of the main lessons is to learn to work together. Maybe that's a good place to end. Thank you.
Thanks. Yes.
Thank you, Emmanuel and Kate. Moving on to the session's third presentation, please join me in welcoming our speakers, Catie Newell from University of Michigan and Zackery Belanger from ArcGeometer with their presentation titled Long Range Intrinsic Acoustic Performance.
I'm first. Hi. Yeah, well, what a great opportunity. Really happy to be here to be able to share these ideas. In a sentence, this project is about a surface that was shaped to draw out the acoustic properties of glass. And this matters because we haven't always had acoustic products, of course. What has always been here since the beginning and is still here today is that the geometric volume of spaces and the shape of their boundaries have always been two primary determining factors for the way that those spaces sound. That is also still true today. This image is one of the interesting moments historically where I think acoustics started to disconnect from architecture. This is the Fogg Lecture Hall at Harvard University, which was built in the 1890s. Its reverberation time was more than twice the reverberation time in the room that we're in right now. It was considered unusable because it was so difficult to understand what anyone was saying in it. Had it been built maybe 20 years earlier, I bet the ceiling would have been coffered. There might have been more complexity on the boundary. That would have helped control the reverberation in the space. Modernism was essentially coming. Rooms were getting simpler. The ornamentation was going away. Our precision was getting better. And reverberation was tending to go up. And this, in the United States at least, is where we started calculating the properties of rooms, and we started to look at the acoustic properties of things we could add to the room. And the 20th century, I think that really set a pace, it set a path for us. And we got very good at efficiently designing engineered surfaces that are meant to be added to rooms. They all tend to work similarly, and they all tend to look very similar. This is essentially where we're at. We unfortunately consider acoustics, by and large, as being outside of architecture, as being a separate line item, something to be added if we have the budget to do so. But this idea of shape is a really powerful one, and you can study it. We have three spaces here, abstract spaces, that all have the same pulse of energy being put into them. So we're watching a wave-based simulation of how sound behaves. Perfectly reflective boundaries, so we're not talking absorption or anything. And as you can see from the left to the right, we have a definite increase in the ability of the space to dissipate that sound energy. We know it's being dissipated because since they all start with the same amount of energy, if you spread them over more of the internal area, it means it's going to be weaker. In other words, the one on the right is inherently better at dissipating sound than the one on the left. And this actually is part of a bigger idea that I call the sphericity conjecture, which is that the further your room gets away from a sphere, the better it will do at dissipating sound. But once you start thinking of sound in this way, as related to shape, it starts to generate some really interesting possibilities and ideas. Here's an abstract representation of a wall surface, which we've doubled to make a corridor to demonstrate this. A wall surface that gets gradually more complex as you go from left to right. And if you let sound go from the center of that and let it develop a little, you see a clear progression of how good this corridor dissipates sound. Where at the left side, you've got a lot of blank space still because we're in the very flat, precise reflective realm. As you go to the middle, the aggressiveness of the shaping goes up. It's more diffusive acoustically, and therefore the sound is more easily or more readily distributed. And this is a little hard to see on the screen, but as you get to the right, the complexity increases even more. We start to open up access to these cavities that we're creating, and the sound actually starts to enter those cavities, effectively being removed from the space. So once you start thinking about the potential for gradient acoustic surfaces and how shape could be a determining factor in this, then you definitely want to build something like this, and you need a really good material to do that.
And so we did it with that surprising material of glass. Glass has this sort of amazing combination of material attributes of being both having hardness as well as light transparency. Interestingly enough, it's one of the rare materials that at the temperature of our built environment is solid, inert, and transparent. Not surprising, though, it has a really bad reputation in acoustics, and that's because, as we see in this room and oftentimes around us, glass is usually in a flat pane, and therefore it's working reflectively. However, the moment you slightly change that geometry, you're changing its relationship to the sound waves in the room. So this gives us the opportunity to look at glass as having the potential to innately build in acoustics, light transmission, and formed bits of enclosure. So we created a demonstration of that called Long Range. Long Range has several geometrical modifications of glass that allow for us to explore how change of geometry can change the relationship to sound. So importantly, a couple of key attributes to it. It's made of two layers, two sides, let's say, that have various curvatures on the different sizes and different compositions. And in doing that, it also has very different internal pockets of air. And during the forming process, we set up a way to have openings that allow access to that internal volume. And then there's a range of scales that are operating in terms of size of the components it's made up of, and then also things like the texture of the openings that's created. Altogether, we're able to put this together. And one of the key interesting things to discuss, and Zach started mentioning it, one of the most difficult ranges of the acoustic spectrum to work with is absorption. And Long Range is able to work with absorption by taking an effort to work with what's called a Helmholtz resonance. Helmholtz resonance is when the opening of a volume and the size of the volume are both together well curated to the frequency, a particular frequency of sound. That causes resonance, which expends energy and reduces the sound intensity. So to do this, we created a system of fabrication that allows us to move the material through many different relationships with sound, even starting with the same acoustic blank. So everything starts with the initial acoustic blank up there on the right. Is there a laser? Well, top left. And goes optionally either being totally solid or we cut in an auxetic pattern using a water jet. Then those pieces are held into a fixed frame inside a kiln. That frame being fixed allows us to have something that makes for ease of assembly, disassembly, and reassembly in reconfiguring the parts. They're slumped and sagged under their own weight, so no hard molding, and instead just the transition through the geometry. The pieces that are solid reach a stable catenary curve. the pieces that we've cut with an auxetic pattern begin to actually unwind and open up. And so this allows us to create those openings that initially were just a single line cut, but because the surface auxetically in its movement is literally unwinding, as we get the depth of the volume we're creating, we also can control the openings that are there with it. So I think an interesting aspect of thinking about the way that we set this up is that, just to reiterate, each piece, as it is going through a slumping position, is transitioning what its relationship to the sound waves would be. So it starts off as flat, very reflective. It actually has a moment of moving to focusing, and then it starts as it gets deeper to contribute more to what would be diffusion. And then the area of getting some openness is where that piece would be able to contribute to the absorption that's happening. Of course, it's also possible to slump it too far or open it too much, then it's going to work transmissively and transmit, or basically kind of transparent thinking to sound. This is part of what we've built into long range as well, but one of the key aspects for control that we developed was where we place the auxetic pattern and also how we, in essence, sort of faded out to constrict that rotational movement that I showed earlier. Then when the pieces are made, it's a lot about the pairing together, understanding what would be the internal volume, the opening or lack of opening, and what the relationships would be in terms of perforations relative to a larger space along the entire surface, and the curvatures, both interior and exterior, as it relates to sound in all of the material condition. Returning a little bit back to the optical qualities, we see long range as the ability for us to also be able to kind of visually inspect and kind of predict and understand how it's working acoustically. We created it with what's called Privigard, made by Guardian Glass. It is a 4mm flat pane that we got as part of their overstock for the automobile industry. It's usually used in tinted windows for cars. And interestingly, so it's a very, very dark green. It even appears black on some of the light qualities. But for us, what became really apparent is that the darker glass allows you to start to see the variation in the geometry. And so it becomes apparent to the kind of knowledge of knowing how the form is affecting the sound. We're able to actually see the subtle differences in our glass to know how that might contribute to the sound that's in the room. So you see an exaggeration of when something is convex and concave, which is also made for the ways that we're dealing with the sizing of the internal volumes and those frequencies. You start to see the overlapping of the perforation and the complexity that comes in of sound either going in, coming out, or reaching that texture. And then obviously also to the things in terms of the layering situation that we have and the sides that are accessible or not accessible based on those perforations, and the different levels of textures that are involved in the system. And then one thing that's super interesting to us, which is hopefully in this image, there's a moment that you can see that's really important in the just the kind of forming of glass, the difference when something is totally flat and then when it gets a very, very subtle curve. And that's the moment where it starts to have a very different relationship from being simply reflective to having the other range of possibilities. So it's a little counter to glass again, usually flat, and then also meant to be seen through, actually not mean to be seen at all, that we use long range as an ability for us to sort of register the acoustic transformations that are possible.
So this is what you have. This is a gradient, left to right. Starts flat, gets more severely curved toward the center, and then on the right, the most severely curved. The idea being that we can move through different areas of acoustic behavior by doing that. I mean, normally, you're probably all aware, but acoustic products are normally sold as categories. You have a reflector, a diffuser, an absorber. So for us to do this all within the same material, the same fabrication structure, really the same, just a progression visually was really important to us. Important to note that these are not individual panels that were all meant to be doing one particular thing acoustically each. Sound is too big for that. Sound is very large. It's our scale. The wavelengths we can hear are this big to the width of this room, probably more. So sound can't resolve these individual panels. It really sees it as a surface. And so conceptually, at least, we expect something like what we see in the diagram on the right, where you get a progression of reflectivity, a progression of diffusion, a progression of absorption and transmission. And these are all happening at all parts on the surface and overlaying with each other. And of course, we want to be able to test it. So this is a laboratory outside of Chicago, and it's a reverberation chamber. We went with, there are two testing standards for absorption, ASTM C423 and ISO 354. They're very similar standards. We grabbed 4 flowers, we call them. So if you just note the order of the colors, the gray, which would be a perfectly reflective one, orange, blue, and black in increasing complexity. This is an image of the blue flower sitting in the laboratory. What we're trying to do is measure for absorption. We did that with all of those. And a very quick look at the data where absorption is on the vertical axis and the frequencies we care about is on the horizontal axis. And the main thing to note is how that order is maintained. Gray, orange, blue, and black. We got increasing absorption from left to right. And we do get some more complicated things happening here. This is what Catie was talking about with Helmholtz resonance. Some forms are better, more efficient at absorbing than others. So this was also expected. Also worth noting, the lab gets less reliable as you go lower in frequency because the sound waves are too large. But this was the big thing we were looking for: the presence of absorption from something like glass, not in fibrous form, and this progression. Back to you.
Thanks. So generally, just a kind of overview of the thought is glass is actually a very unusual and unexpected material for us to be considering how it's working acoustically. And so we really wanted to use long range as the ability to demonstrate a lot of what Zach was talking about in terms of how the subtle change or the intentional change of geometry can actually do a lot to acoustics. And that there's the opportunity built into the sort of material process making and form making to be one of the drivers in a condition where we're actually building in the kind of intrinsic relationship to acoustic from the onset, and can see this as being something applied to many different materials, asking for them to be doing having more behavior and more performance within their setting. So with glass, we were able to get light transmission, the intrinsic acoustic properties, and working through moving it towards a kind of formed enclosure. And we anticipate this as being something that's possible in so many different materials. Thanks.
Yeah, thank you.
Thank you, Catie and Zackery. And so our last presentation by Sandy Curth from MIT Department of Architecture will be presenting Sueños con Tierra y Concreto. Welcome, Sandy.
Thank you. Hello, everyone. Thank you for being here. We're honored to present in such good company. I'll be sharing a project that we completed about 2 years ago in Mexico City with a great team, Eduardo Gascon, Kylie Fikert, Dinora Schulte, Mohammed Ismail, who's also here, and Professor Caitlin Mueller. Mohammed is now a professor also, I should say. Let's go back one. So this project was the result of over 3 years of conversation and collaboration between our team and a variety of stakeholders in Mexico, including News Story and Echele, which are essentially large-scale manufacturers of low-cost affordable housing. They're nonprofits. And the LCAU, Center for Advanced Urbanism at MIT, as well as Mota Engel, a large construction company in Mexico. So what we produced is basically a small single-story prototype of housing that we used as a messaging board for the couple weeks of the Mextropolis Architecture Festival for people to be able to share their dreams about the future of urbanism in Mexico. So this whole project is essentially built around an existing model of incremental housing produced by New Story and Etchelet that utilizes something called eco-blocks, which are basically compressed earth blocks for walls, and a beam and block floor system. So after many conversations, we decided that the place where we could best engage in their process and really contribute something is in the floor system. As you all know, buildings are bad for the environment most of the time. And specifically, the structural systems in buildings tend to account for 60 to 80% of that carbon impact. So really, anything you can do to cut material out of the floor of a building has a direct impact on climate. So here we took the traditional beam and block fabrication system that is super common throughout Mexico. It's been in use for at least 50 years. The key advantage is that it's human assemblable. You don't need any heavy equipment. So 2 workers can lift a beam into place, and then 1 worker can stand on those beams and place the blocks. And these blocks are typically made of concrete that is precast or of an extruded ceramic. So our pavilion is quite simple. We just took their existing wall system and put a floor on it that used about half as much material. So a 50% reduction in concrete in the floor system without compromising the structural performance at all. So this is a code-compliant innovation. And I'll just point out that while we didn't have a chance to load test the individual components, the prototype did survive a 6.8 magnitude earthquake in Mexico City 2 days after it was constructed. And I was standing right next to it. Nothing broke. And when I talked to Mohammed Ismail, our lead structural engineer, afterwards, he kind of looked at me and said, well, yeah, I mean, I designed it to code. What did you think would happen? So some load testing. So the system is made up of prefabricated shape-optimized beams, which I'll explain a little bit more later. These were cast in a fiberglass mold, which was produced by a manufacturer in northern Mexico, in Monterrey. They typically specialize in large-scale sculptural fabrication, and we chose to work with them because they could produce such a high-quality, high-tolerance mold, which we can reuse up to 200 times. Then on the block side, we just used the standard compressed earth blocks of our collaborator Etchelet, and we post-tension them because we couldn't install foundations or anything because this was a temporary pavilion, and we needed to do that to make it safe. And then to span between the beams, we produced mass-customized 3D printed clay blocks, which was more my role in the project. And these were manufactured by Manufactura, the company of our collaborator Denora in Mexico City, using locally available ceramic materials and expertise. So kind of already touched on the blocks. I'm going to skip through that. Our methodology for developing this material reduction strategy for the beam and block floor was to integrate structural requirements, material parameters, and fabrication constraints into a very flexible and iterative model. So as we worked with our collaborators, we could just very rapidly update our design, which had major advantages. So we'll talk about the beams in a second, but the blocks were form-found using graphic statics, and they essentially vary in depth across the span to maximize the material savings in the concrete elements. So shape optimization, if you're not familiar with this concept, is essentially a technology that allows us to reduce material very kind of in a tailored fashion across a structural element by taking variable cross-sections and doing a full analytical model that takes into account all of the concrete mechanics for each of those slices, and then basically sculpting that structural element into a unit that has only material where it's needed. This model does take into account, the steel, the building code. So we basically start with the building code and work up from there. And this is the product of many, many years of work by Mo and Caitlin Mueller. So you can see that essentially what we're doing here is starting with a flat slab, which is kind of the least efficient option, and then moving up to various levels of optimization that cut varying degrees of material without compromising structural performance. So we opted for the third version here, which is essentially a fixed width beam and block system, but with variable depth. And we did this to facilitate ease of fabrication. You need people to be able to fit between the beams to assemble, so having variable width was a little too complicated for this particular prototype. And we'll talk a little bit about what happens from a thermal perspective at the end, and I'm very inspired by the last talk. I'd love to, at some point, touch on the acoustic performance that a system like this could offer. So shaped concrete beams, this is what they look like. You can see that they can easily be placed on top of our prototype by 2 people, just stepping on scaffolding, so they're quite light. I moved a number of these, and I'm a very weak grad student who spends all my time typing, so I can attest to their lightness. And then onto the 3D printed clay blocks. This was the part that I was primarily engaged in. This was a super fun project because we basically got to a few months from completing the prototype, or completing the design of the prototype, and realized that to really maximize the efficiency of the system, we needed variable geometry to span between the beams. So we started thinking about how to engage the traditionally used material, which is essentially a terracotta. It's a sand-rich clay that has pretty good structural performance, enough to hold up the topping slab. So when you complete the system, you pour a thin topping slab across the beams and the blocks act as a lost formwork. So we began working out how to make a high tolerance system. So these blocks started out in California, where I prototyped them in a different ceramic material. Then we began working to calibrate the material in Mexico with Manufactura and another collaborator called Anfora, which is probably the largest dinnerware manufacturer in Mexico City with over 100 years of experience in ceramic materials. So they helped us source a really nice clay that's a mixture of materials, like volcanic materials from Zacatecas and ceramic materials from Oaxaca that is very standard in these systems, but we made a nice mix there. And then we spent the time to really calibrate a high precision system. And this precision really allowed us to make a high tolerance, code compliant floor. We allowed about 5 millimeters on the edge of each block with room for the beam so that when you cast, you don't have any gaps, anything like that. And now we have our mandatory robotic craft video, which I'll talk over. So we didn't need a whole lot of clay. This was kind of a small prototype. It was about 250 printed blocks, 18 unique designs. So we just mixed the clay up the old-fashioned way and produced a very nice homogeneous mix using a technique that is probably, I don't know, at least 10,000 years old. And then some of you who I'm sure have gotten into clay printing at this point are familiar with this process. Loading tubes full of clay, de-airing the material so that you don't have any voids that would cause explosions in the kiln. Of course, there's more industrial ways to do this now. We could mount multiple extruders on the robot. We could use more of a gantry-style printer. But for our purposes, this was great. And these were manufactured about a 15-minute walk from the site of the assembly. So it was nice to work with such a local fabricator. You can note that we're printing on plaster here, in part to ensure that we get really consistent drying. I'm sure if you've ever played with clay, you know that drying and shrinkage are a major issue, and we wanted to ensure that we stayed intolerant, so we really controlled the rate at which these were printed and the rate at which they dried and were fired. And you can see that they really vary in depth, and that's part of what allowed our material savings. I think there's also probably some interesting thermal benefits to talk about in this block design, but we didn't do any simulation or modeling to understand that, so that's part of our future work. One other note I would make is that understanding the embodied carbon of fired ceramic is quite challenging because it's mostly dependent on the grid mix that is used to fire the objects. The material itself is very low carbon. So here we're firing low temperature and electric kiln, not super high impact, but we don't know the exact quantification. It's probably very similar to the standard ceramic blocks used for this system. So here's the final little structure. About 2,000 people interacted with it over the course of 2 weeks, and something that I really enjoyed talking to folks about was how they felt like it was recognizable. It looked like something they were familiar with from their own buildings, which honestly is a very important aspect. As many of you know, we may love crazy looking things, but most people want to live in a house that looks like something they're familiar with. So it was nice to hear that to contractors and residents, this felt like a familiar, reasonable system. Okay, so just a couple key takeaways, and then I'll show a few future-looking pieces of research. Beginning our design process with stakeholders is what made this possible. We literally talked for 3 years before we made anything, and obviously what we produced is basically a simple and incremental advance in an already existing system. And what this means is that it's readily deployable, and as I'll touch on in the end, we're already starting to mass manufacture this system. Overall, 50% reduction in carbon from the concrete perspective. Printing local clay, was possibly not the most scalable, right? 3D printing is kind of slow, but it did allow us to manufacture this prototype extremely quickly. So it was really good for demonstrating what was possible. And then just to end on, of course, local partnership is what enables this kind of high quality code compliant fabrication. And it allows us to situate our work in a way that's really relevant. So I'll show a few more projects. These are some alternative beam forming options that Mo has developed over the years. This is a project from India where they produced quite a nice shaped beam using a steel formwork. He's also developed some interesting lower carbon formworks like this bamboo option. I found this one pretty exciting. And my own collaboration with Mo is on large-scale additive manufacturing with earth. We made this beam about a year ago, and it's fully 3D shaped with completely recyclable formwork. You can just directly reuse the mud. Conventional reinforcing and code compliant for building code in California. There's that finished beam. This is part of a larger system of reinforced concrete casting systems using printing that don't waste any formwork. That paper will be out very soon, I hope. So final point I'll make is that you can also integrate thermal performance without compromising structural performance. So our colleague, Eduardo Gascon, who led a lot of this project, has developed a shaped slab system that has radiant cooling. Of course, this is a parameterized design, so there's many good options that you can choose from, which have perhaps different aesthetic or acoustic performance, all of which are structurally functional and have relatively low embodied carbon. And I'll just end on the note that we've now formed a company with this team and are in the process of manufacturing our first production scale beam and block system that is shape optimized. We have a partner in northern Mexico, and just a couple weeks ago they sent us the first pictures of the first casts they've pulled. So hopefully we will actually be making real buildings, maybe even in the next year or two. So thank you all. Appreciate listening and happy to talk after the discussion.
So thank you to our panelists for, and as well as our keynote this morning for an outstanding series of presentations. So we'll now invite our speakers here to join us for a discussion. Is there enough chairs? Oh yeah, no worries. Yeah, maybe. Yeah. Okay. All right. Wow. I mean, following these remarkable presentations, the range this morning, I think each project really underlines a unique interpretation of localizing sourcing. So I feel like together with your work that explores various aspects of localization, you guys have touched upon cyclical processes, the delicate balance between creativity but also compliance, right? Whether they're related to materials or sound frequency, technical means that might be high-tech and low-tech, labor and building codes. And so maybe to get it started, reflecting on the conference theme, the future of fabrication in a resource challenge world, and especially what Indy brought forth this morning on how we design for a 3-degree extra future. Could each of you speak a little bit more to the opportunities of local thinking, knowledge, and collaboration could afford?
I'm happy to start. So I think in our project, the sort of key local aspect we're dealing with is that material is the main driver of cost in Mexico and in much of the global south. So unlike Europe or the United States, where labor is what makes a building expensive, we have a lot of opportunity, for instance, in Mexico, to really lower the cost of housing and lower the embodied carbon of buildings just through material savings. So finding out that factor from our collaborators and then spending years basically developing a whole workflow just to address that, I think is what allowed us to make an impactful project. So, there's the local collaboration on a material scale, like figuring out which materials to access, which fabricators to work with, but then there's sort of the meta, like country scale or state scale, localized knowledge that you require to make something that really functions in a local economy as well.
I guess from our perspective at Hook Park, we inhabit an industrial woodland, so we experience the processes and we could kind of intervene, and we see the waste material, so that locality is really immediate. So the perceptions are really quickly drawn. We are confronted with the material that's left behind from an industrial harvesting process. So the challenges it's not that hard to kind of draw that conclusion.
I think as well, it's the collaboration is really key. So I think if we're looking at, because we're confronted with the full spectrum of the supply chain, we need to engage with kind of cross-disciplinary conversations that allow us as designers to see the full picture of that. And I think that is probably the most critical thing in terms of how we address the projects.
I think we might take on a definition of local that really thinks a lot, very local to a particular space. And part of the sort of asking of the performance of the materials to take on more things also is embedded in the understanding that if we make spaces that are better, are more comfortable, have a different longevity, then there's actually that's one effort in producing a better world, using less materials, caring for the spaces, is to make things that really, really work and aren't, for instance, torn down because they don't sound good or don't look good, or a factor that can't be switched out.
From our perspective, what's really still interesting for us to investigate is understanding the household water treatment practices as a lived experience. And we often take for granted, obviously, tapped water supply, and we take for granted how much our buildings are doing. So in a sense, a lot of the inquiry that we can still forge ahead with is understanding that balance between locally sourced materials, something that someone would grow on site, extract to create the dye that's part of the treatment process. But you're also now wanting to have that balance of having security as a sensibility. You understand that there's enough soil energy for that day to treat the water effectively, but you're not burdened by that consideration. And the visual indication is something that assists with feeling that awareness of the water is being treated, but it is also part of the fabric of your building. So you have the security of your space, but you also have the daily practices that, that would actually allow it to take place.
Yeah, and I would just add to that it's really a recoupling of human metabolism and metabolic flows with available bioclimatic energy flows. Because in the different locations where we're testing, firstly, it's the cocktail or the combination of the solar concentrating geometry in association with the plant-based photosensitizers that allows you to reduce the sterilization time, for example, from hours to minutes, which is absolutely critical in climates that are aleatory, and you might only have like a solar window of like half an hour, and you've got to be able to get safe water within that window. So it really is, in a sense, a completely different stance. You can obviously you have a visualization of your own bodily sort of metabolism in a building envelope or in an environment, and it's in interfacing with exactly what that climatic resource is, and that visibility is something sort of new and different.
Thank you. And I think the sort of different time frames that you even Anna, you just mentioned, reminds me of Mette's closing remarks of your keynote yesterday, where she highlighted the notion of transferability from the interscale to the multi-scalar for 21st century world of design. And I think this notion actually really deeply resonates with the presentation this morning, because as localization implies a kind of spatial, and perhaps it could be geographical, it could be material, it could be geometric, some sort of restriction and limits, right, like localization. And so I wonder, where does the local end in your work, and how does it relate to the global? And so in other words, how does transferability integrate into your highly localized design and fabrication efforts?
Well, our system proposition is a provocation to look at the building envelope and our existing built environment as a rich space where we can embed lots of functionality. And really, in showing a really simple modification to an existing roofing typology, it's demonstrating a way that, some kind of reproducibility, replicability can be leveraged in different sites with different assembly logics, different materials. We focused on particular field sites, but the same logic applies. So really towards that, it being an approach-driven proposition, as opposed to, the embodiment itself lends towards greater distribution. And then that is the shift from local to global, ideally. Just the shift in thinking of what our water systems and our energy systems in buildings could look like.
And maybe I could say a few things acoustically. I don't know if this is exactly what you're getting at, but I'm gonna say it anyway. That I think historically and acoustically, we've gotten in the habit of considering acoustics to be these individual units that are brought in and that are very separate, and that we try to avoid and minimize, and therefore they're made to be as efficient as possible. And but really, they're just a part of the room. They're a part of the whole room. So to me, this idea of local and global is also fairly local, in that when you add anything to a room, you're changing the shape of it, you're changing the sound of it, and if we can think about how we might shape the boundaries of the room without having to bring in outside materials, then we're really doing that in service to the entire enclosure. And it could go beyond that, because if you explore this with certain materials and it applies to others, you suddenly have the ability to apply this kind of thinking wherever you are.
I mean, I think we're obviously, it's fairly unusual to have your own landscape supplying your building materials literally right next to where you're making the buildings. But I think it suggests a kind of way of thinking that the associated, with everything we make, buildings, technologies, everything, there is an associated landscape that comes with that, an associated set of environmental conditions, associated set of material processes and material narratives. And I think that can obviously operate very neatly for us at a very, very, very local scale. But I think equally, if it's within the thinking of a designer, it also operates at a global scale. But it's like the piece that we seem to have forgotten to talk about for a very long time, the shadow of whatever we're making. I guess it's how can that as a mindset, I mean, we're educators. I think one of the most fundamental things that we do is education, maybe more than research. How can we shift slightly the conversation, a different way of thinking about the things we make in relation to a whole set of other interconnected and interrelated entanglements?
But on a finer grain kind of perspective, really, if you look at timber production, we have to shift this perspective that we're only going to use the nut-free bits of timber, right? There is not enough timber to go around as a kind of, so we have to reevaluate and rethink how we perceive our material resource. And that's kind of the shift that we're trying to implement. Like we can use 40 to 50% more of a tree than we currently do. So that's kind of a challenge. It's maybe a small step globally, but it's a shift in kind of perspective.
I think that touches a little bit on, like finding the right driver for a project. So I know in our example, we're using a super generalizable, essentially almost material agnostic set of computational methods, but to do a super highly specific thing that emerged as a need from our stakeholders. And so, for us, what drives the project is a desire to reduce embodied carbon. But for instance, for the manufacturing company we're now partnering with to mass manufacture this system, they think that's cool, but what they really care about is that it's half as much concrete. So, they can put more beams on a truck. They can sell more of the system. They could lower the price, right? So really finding the balance between an economic driver or some more academic goal is pretty important, and also just showing that alignment is totally possible, right? Like, there's no reason you can't make a cheaper, better thing for less material and have like a positive cost and climate benefit.
Yeah, and I think in all the work, the technology, in different degree, high tech to low tech, it becomes a route to then create replicability. Like, there's replicability in all your work, from material to joineries, and then to also the scale of the communities. So, and so I think maybe we can start opening up to the floor, to the audience, if we have any questions. Yes.
Hello. I'm going to try and phrase it so that my question makes sense. But like reflecting back on the talk that we had from Indy Johar, and I think one of the things he was talking about was this need to radically reduce our materials and go thinking deeper and broader on the choice of our materials, and that not just being the materials of the final thing that we've made, but all the stuff and the technology and things that we're using during the production process. And also going deeper to think what is the researchers and the research project's foundational goals, and what are we actually trying to change. So I was wondering if you could all reflect on your project from the context and the perspective that Andy gave in his talk.
I mean, I suppose we're really simple. We're just trying to make a lot of really affordable housing very fast. I think everybody kind of knows that fact about how we need to produce something like 90,000 square feet of new livable floor area every day between now and 2050 to house all the people who will need housing in cities by 2050. So I think there's an urgency to that, and that really drives our research. So maybe, in many ways, I almost feel like our research is getting more and more boring because we're getting super practical. We're just finding like little tweaks and things that work with existing manufacturing that can be implemented immediately, which is quite a challenge. Often finding a way to make a system implementable immediately is far, far harder than anything you're trying to do with a robot or, even the material science that goes into a project.
I think there's two things that stand out from the talk that was, really thought-provoking. In that, one being the mundane, everyday of our built environment, the role it plays. So kind of talking about the change we need to make is really fundamental. It's not. It's radical in its simplicity and like really what we need to shift in terms of our priorities. The second, and therefore, as an example, our proposition is really just a simple reorganization of material properties we already have in our buildings, but they're just interfaced in a way that we're not just rejecting available solar energy, but we're shaping it for multiple functions that actually also qualitatively think about what we need when we live, be it visual comfort, thermal comfort, and the sense of security. The second thing is that relationship with us and our bioclimatic flows and our environment. That it's not, we're not putting our environment to work. It's not. It's an engagement. It's an interface between the building and a particular climate, as opposed to, like, for example, with the centralized infrastructure systems that we have become very familiar with. They are an imposition on the environment. They are totalizing, and they have actually basically brought about expectations from the environment that is not sustainable. And I think that bio-agency that Indy referred to is really important.
I think that the part that really resonated for me was when you were talking about the agency of designers and the potential for designers to engage in you were talking about the full spectrum of the problem. And I think that for me that was really incredible to hear in terms of just the role of design in relationship to all of the other kind of structures that have been created around us, and the possibilities of this, of breaking out of a kind of quite a tight disciplinary boundary that we have as architects and designers, to find a broader definition of design and a more integrated, I suppose, mode of operating as designers that again takes in or tries to take in a bigger kind of realm of where we're operating. So in in our case, that relates to kind of the entirety of a supply chain, but I think it can operate on a whole other lot of levels. And that brings with it, like we said, this notion that we need to collaborate across disciplines in order to make that achievable. And I think that's what resonated the most with me, is we have a lot of ingenuity and agency, and we always talk about the fact that actually young designers are amazingly ingenious and brilliant, and they can solve fantastic problems. We're not necessarily given the right problems, or we're not looking at the problems in the right way or in broad enough terms to be able to address them.
I think something that really resonated with me was a concept of care and a concept of time, and I think those expand in so many different definitions. And I think a lot of what we are all doing is working at quite a quick pace to kind of prove ideas that can happen, but adding on this sort of extra layer of to what extent this can care for what's already there, what's going to be there in 1,000 years, how do we redo something or undo something. I think is a really sort of extraordinary way to have to then look at both our materials and our processes of making and ask for them for such a duration, but a sort of let's say an emotional shift to care more than anything.
Thank you. Other question? Yes, Mette.
Thank you very much. I think one of the things that I've been thinking about this morning is
maybe coined very well by you, Kate and Emmanuel, when you were talking about this idea that the canopy is not really used. And I was just thinking that in our work with these biopolymers that we also showed yesterday, we understand that there is no such thing, that we need to really reconsider this idea that there might be a waste stream or that there might be something that is surplus. And I assume that you say that, but you know otherwise because you're there in the forest and you know what the importance of all of this debris as it falls to the ground, what it's actually performing. But I was just wondering if it was possible to make that idea bigger across the panel. So what is it, when we are using resources, when we are trying to identify what we call waste streams, but streams that are deployed differently, or change the deployment of these waste streams, how is it that they become part of, or how do these intersections disrupt other kind of ecological balances? And the reason I want to try to unpack it a little bit was because this idea of the photosynthetic ceiling also, that we know that the photosynthesis on our planet is constant. So when we start deploying photosynthesis in other systems, whether they are forestry or whether they are water purification systems, even at that scale we are also changing balances, both locally and globally. And I was just wondering, what do you think about how we account for this? Like not sort of like, okay, now I've used 2 points or whatever, but sort of how do we engage critically with how these balances are being moved, and how do we take maybe not responsibility, but just ethically engage with that kind of space?
I mean, I would point out that those small diameter roundwood timbers that are left on the forest floor aren't waste in terms of the forest, because obviously they provide an amazing ecological service to the forest. They decay and they become soil. So I think that's kind of a wider, more complex conversation than we had time to go into, but it is this thing of, I don't know what the answer is, but how can all the values appear on the balance sheet, I think, as you mentioned this morning, not just the economic values, but even just in economic terms. In economic terms, for forestry, it's waste. But it's not in all terms is it waste, and I think that's a really interesting conversation to have.
I think maybe a little bit, just thinking specifically for glass, which clearly uses a lot of energy being first made. The creation of new glass seems like the waste of this moment, especially when we're talking about things being brought down, glass that's in existing buildings. And I think we have pushed a little bit in the example of how acoustics could affect, the shaping of different materials could affect acoustics. There is also the consideration of basically harvesting glass that's already flat and not doing a good job, and remaking it so that when it's used again and not made as new glass, it's actually being used for that much more of a performance, and ideally that much more of a sort of lifespan or literal experience of our buildings.
Actually, I need to apologize. I think I might have used the term waste last night, and our collaborators would not be happy with me with that term, because it is true that it's a very anthropocentric term, right? The one question, though, in that sort of appraisal of values is, let's say from the standpoint of climate change, if forests are very stressed, and we sort of allow for, so they're just as stressed out about climate change as anyone else, right? Or climate breakdown, I guess we're talking about, human-induced climate breakdown, and that they actually probably need a lot of tender loving care, don't they? And to take out some of this biomass, even that gorgeous, I was looking at that gorgeous picture of the tree, and of course as humans we're incredibly attached to this, right? Because we think it's incredibly precious, and it has a registration of time that is sublime. But in truth,
that tree is probably stressing out the forest, right? So that tree needs to go from the standpoint of the forest if we're thinking about it from the perspective of accelerating the carbon sequestration or amplifying, let's say, the forest productivity, if you will. These are all anthropocentric terms, it's true. But I think we just have to be very discursive, don't we, about the expansion of value frameworks and how exactly we're valuing and what value do these material flows have within our current context. And we can look at it from a lot of different standpoints. Leaving a lot of that stuff on the forest floor is going to produce obviously a lot of methane and other accelerating climate change effects. So if that is the priority to accelerate carbon sequestration or reduce climate change effects, then we would probably choose to call that rather than allow it to decay and do its beautiful work for, let's say, the regeneration of the soils and everything. And so because I'm really also very moved by Indy's keynote and just how he's talking about soils, he's talking about everything. I mean, soil is the basics. If we don't have soil, then we're nowhere. So there's a lot of very complex trade-offs, per your point. Thank you. So.
And maybe on that note too, to Meta's question, Indy, you talk about like we need to use material. It's all about efficacy, and I feel like in the work here, that when we're talking about sourcing and performance, that we are asking the material to do more. We're asking them to do a plurality of performance, which I think is evident in all the projects here, like taking light and transforming that, and then to create other materials, water in this case. And so, yeah, thank you for the question. Any other question? I think we're close to time as well. And just wondering if, Indy, if you might have any sort of closing comments for this panel discussion.
Sure. A few things that I found really interesting was, I think if you look at all the work that's going on, I think one of the big questions for us is how do we imagine standards for this economy? Because if you're going to go for hyper-localized or very local construction capabilities, we're going to have to reimagine our standards thinking. So if we're going to use complex, rich, highly local particular timber, we have to reimagine standards frameworks. And what our standards frameworks drive massive amounts of redundancy into our material economy, and they drive a type of uniformity. Now we have the computational capabilities, we have capacities to reimagine standards. So what I suppose my big encouragement would be to think about the material technologies that we're building, but also the institutional technologies that are actually critical to unlock those material economies. There's some really brilliant work done on kind of new material capabilities, like the efficacy of material, to be able to use material, highly particular material. So who's it? Emmanuel de Lander's work on 1,000 Years of Nonlinear History, beautiful material philosopher, because he really talks about the difference between a katana, which was particular to that iron, as opposed to the generic sword, which is particular to iron as a whole. So if we're going to, and we now have the technology to be able to create a new digital craft economy, which is highly particular and highly localized to that material in that context. That capability is now available to us. So it's a kind of a new age of industrialization, which is rooted in high particularity. So that's one dimension that I just would encourage us to involve in. The other thing I would just say is that, just as a material conversation, yes, our buildings are 50-factor over-engineered, planes are 10-factor over-engineered. So how do we reduce the net material demands of material buildings as a whole? Massive impact, right? Second is, how do you make our buildings massively durable? So in Denmark, the average lifespan of a modern building is less than 25 years now. So how do you do that? So durability. Then there is a key question about deconstruction and reconstruction. If you can make buildings deconstructible and reconstructible, that is really critical. And that requires material passports, warranties, all sorts of things which are really the problem. It's not a technical problem, it's an institutional problem. And then finally, obviously, the regenerative components, which has all the richness of how do you really make it regenerative in terms of actually the soil that it comes from, and all the deeper questions on the table. So my only thing would be, how do we complement all the amazing work that's happening on the panel with all the institutional work that's really required? And that's a real invitation to everyone here to think about all the adjacent technologies that are required to make these realities true and scalable and deliverable to the world as a whole. So thank you.
All right. Thank you. Thank you, Andy. Thank you, Andy, and thank you to our panelists, and concluding this third session.